This presentation will describe how to use the conservation of power to solve dynamic force analysis. We have 3 examples. In the first example of 4-bar liquid, all positions of joint points are given. According to given angular velocity omega-2 and the acceleration alpha-2, we compute the angular velocities and the angular accelerations of member 3 and 4. Through velocity analysis and the acceleration analysis, then the velocity and the acceleration and the center of mass of each member can be determined. The results are given in the last lesson. Dynamic effects are considered. In this case, we need to find the output torque, tau for 1. First, we sketch the force diagram of this mechanism. Here, external loads and the initial loads are involved. For conservation of power, we don't need to consider internal forces. For example, forces in coordination joints A, B, C, and D. Now we have 3 forces, W2, W3, and W4, and 3 torques, tau12, tau13, and tau41. Only the output torque, tau41, is unknown, so we can use the conservation of power to determine it. According to given omega-2, we use velocity analysis to determine the angular velocity of omega-3 and omega-4, and the velocity of points P, H, and Q, which the weights W2, W3, and W4 acting on them respectively. According to given alpha-2, we use acceleration analysis to determine angular accelerations of alpha-3 and alpha-4, and then to determine accelerations of points P, H, and Q. In this case, dynamic effects are taken into account. Since accelerations are known, we can compute the initial force Fp, Fh, and Fq, and the initial torques Cp, Ch, and Cq. Finally, substituting all known values into the conservation equations, we will get output torque tau for 1. This slide shows you how to determine output torque tau for 1 for this case using the conservation of power. For conservation of power, we know the sum of powers generated by the forces and the torques equal to 0. In dynamic force analysis, additionally, the dynamic effects need to consider. That is initial forces and the torques of members. They will be regarded as external forces and the torques acting on the members. Here we have input torques tau12 and tau13, and the weights of member 2, 3, and 4. Here torque tau14 is unknown. Initial forces and the initial torques of members are computed, and their values are listed here. Then we substitute all the forces and the torques into the conservation equations, of course, including initial forces and the initial torques. They are colored as red in the equation. It is easy to solve the problem using an equation. We have tau for 1, 366.8 Newton-meter in the counterclockwise direction. This example is a slider crank mechanism. According to the given parameters, we do a kinematic analysis to get the velocities and the accelerations which we concern. In this case, we need to find input torque tau1 2. We have torque tau1 2 and force F14 and weights W2, W3, and W4. Here, input torque tau1 2 is unknown. We use velocity analysis and acceleration analysis to determine velocities and accelerations of points we concern. Then to get initial forces Fp, Fh, Fc, and the initial torque Cp and Ch. Finally, we use the conservation of power to solve torque tau1 2. Again, we use the conservation of power to do dynamic force analysis on this mechanism. The input loads and the initial loads are listed here for this case. Substituting all the loads and the velocities into conservation equation, we get input torque tau1 2 equal to 62.6 Nm in the clockwise direction. The last example is a double slide mechanism. Again, according to the given parameters, we do a kinematic analysis to get the velocity and the accelerations which we concern. In this case, we need to find output force F41. We have input torque tau1 2 and output force F41 and the weights W2, W3, and W4. Here, the output force F41 is unknown. We use velocity analysis and acceleration analysis. We can determine the velocity and the acceleration of every point in the mechanism. Then to get initial forces Fp, Fb, and Fc, and the initial torque Cp and Cc. Since velocity and angular velocities are known, again, we use the conservation of power to solve output force F41. Here are input loads and the initial loads in this case. Substituting the loads and the velocity into the conservation equations, we get input force F14 is 3,113.2 Newton to the left. Well, we take 2 weeks to talk about static force analysis and the dynamic force analysis for mechanisms, and use 2 methods: free body diagrams and the conservation of power to solve forces and the torques of mechanism. These 2 methods are very useful in practice. I hope you can well know them by practice the problems of homework. See you very soon. Bye bye.